In this basic organic chemistry class, we are going to be looking at carboxylic acid. At the end of this class, you'll be able to understand what carboxylic acids are, how to name them, their properties, the effect of substituents on carboxylic acid. You also understand how this carboxylic acid can be prepared, their reaction, how you can identify them in the laboratory, and some useful carboxylic acid around us. Carboxylic acid are organic compounds that contain carboxyl functional group. This carboxyl functional group is a combination of carbonyl functional group and hydroxyl functional group. So carboxyl functional group is made up of two functional groups, which is carbonyl and hydroxyl. This carboxylic acid can also be divided into mono, di, or tri. So when there is only one carboxyl functional group in a compound, we call it monocarboxylic acid. We also have dicarboxylic acid, but tricarboxylic is available, but not as common as mono and dicarboxylic acid. Like explained in the previous slide, the functional group is highlighted, the carbonyl is in green, while the hydroxyl is in orange color. Carboxylic acid are not as strong as HCl and sulfuric acid, which are inorganic acids. These carboxylic acids are weak acids. In water, they ionize to produce carboxylate and hydronium ions. They have capacity to lose proton because the two oxygen atoms in carboxylate ion are stabilized. In the presence of electron withdrawing group, this electron withdrawing group is going to disperse the negative charge on this carboxylate ion by resonance and inductive effect, thereby stabilizing the carboxylate ion. In naming, IUPAC system is employed in naming carboxylic acid. In this naming, the E in alkane is replaced with oic acid. When carbon is 1 and 2, the common names are formic and acetic acid, while their IUPAC name is metanoic for carbon 1 and ethanoic for carbon 2. Remember, the ethane forms ethanoic because the E in ethane is replaced with oic acid. When there are substituents in carboxylic acid, naming them, you're going to consider the carboxyl functional group, the carbon of carboxyl, to be carbon number 1. Then you name the same method of naming hydrocarbons. The only difference is that my carbon 1 should be the carboxyl functional group. When naming, unlike alcohol, I will put 1-ol because the carbon of carboxyl is carbon number 1. There's no need to indicate the number when naming carboxylic acid. So in the first structure, my alkyl, which is methyl, is carbon number 3. And the number of carbons is 4, making it buts. So I call it 3-methyl butanoic acid. I will not say 3-methyl butan 1-oic acid. No, it is not that in naming carboxylic compounds. When there are more than one carboxyl functional group in a compound, we call it dioic. Example is ethane dioic and propane dioic. In that case, you name the alkane. The number of carbon is the alkane. Now, the first one, the carbon is 2. So I'll call it ethane. Then in that ethane, I have 2 carboxyl. So I call it ethane dioic acid. When the carbon is 3, it is propane. But because there are 2 carboxyl, I'll call it propane dioic acid. Remember, in mono, you don't put the E. You replace the E with oic. But in di, you put all the alkane, then add dioic at the end. I hope you understand the difference between the two. Physical properties of carboxylic acid. The carboxyl group contains three polar covalent bonds, which are the carbonized CO, the CO that is available in ether, and hydroxy group. So these are the three polar covalent bonds in carboxyl functional group. Carboxylic acid can have both inter and intramolecular hydrogen bonding. So it has strong hydrogen bonding. And because of that, they have higher boiling point than other organic compounds of comparable molecular weight. Liquid carboxylic acid have sharp and disagreeable odor, just like the one you experience in vinegar. Vinegar contains at least 4% of acetic acid. They have sour taste. That's the taste you feel when you're taking lime or lemon. Acidity of carboxylic acid. When they ionize in water, carboxylic acid is going to form carboxylate and hydronium ion. Then when you want to form the equilibrium, remember equilibrium is product over reactants. But because water is regarded as unity, so that's why our equilibrium is product over carboxylic acid. That is carboxylate. Hydroxyonium ion is represented as hydrogen ion, then over reactant, which is carboxylic acid. pKa is minus logarithm of K. So for acid to be strong, it's going to be low pKa and high Ka. Because of that, we realize that from pKa value, that carboxylic acid is stronger than alcohol in acidity, because the pK of carboxylic acid is between 4 to 5, while that of alcohol is between 14 to 16. In ionization of carboxylic acid, there is corresponding the localization of negative charge by resonance, and this is not obtainable in alcohol. Hence, trying to validate why carboxylic acid is more acidic than alcohol. There is difference in electronegativity between the carbon and oxygen in carboxylic acid. This difference is what induces polarization of hydroxyl bond. Then because of this, the presence of electron withdrawing group is going to weaken hydroxyl group and enhance the ionization compared with that is obtainable in alcohol. About the effect of electron withdrawing group on carboxylic acid. Electron withdrawing group is going to stabilize the carboxylate ion. Remember, carboxylate ion is full of negative charges, which is electron rich. So when you withdraw, it becomes more stable, hence making the acid stronger. But when you donate, when there is excess negative charges, you're going to destabilize the carboxylate ion, making the acid weak. Electron withdrawing group like NO2. The presence of this NO2 is going to make this acid strong than normal carboxylic acid. So when I have carboxylic acid and I have nitrocarboxylic acid, nitrocarboxylic acid is going to be stronger than normal carboxylic acid because of the electron withdrawing effect of the nitro group. But when I have NO2 in auto, meta, and para, auto is going to be more acidic, followed by para and meta, because auto and para are going to have both inductive effect and mesomeric effect, while meta is going to have just only inductive effect. Electron withdrawing substituents like halogens are going to increase acidity of carboxylic acid because they are going to withdraw electron density from this carboxyl group. Remember, there is excess electrons because of negative charge. So when they are withdrawing this electron density, they are going to increase acidity of that carboxylic group. The same thing, when there is electron donating group, they are going to increase the electron density, thereby destabilizing this carboxylate anion and making the acidity to be very weak. That is why carboxylic acid is a weak acid. Then when I add chlorine, it becomes acyl chloride. It becomes more acidic than the carboxylic acid. And when I'm adding amide, which is electron donating group, is going to weaken the carboxylic acid and make it weaker than normal carboxylic acid. So, explain the effect of substituents on aliphatic carboxylic acid. The method of preparation of carboxylic acid. The common method we know is oxidation of primary alcohols and aldehydes, oxidation of alkanes, hydrolysis of nitrile, hydrolysis of ester, carboxylation of Grignard method, carboxylation of alkane. It can also be prepared from malonic ester. So we're going to look at this method of preparations one after the other. In oxidation of primary alcohols and aldehyde, when primary alcohols are oxidized on a normal norm, they continue oxidation until carboxylic acid is formed. So, the intermediate in this reaction is an aldehyde, which further oxidizes to carboxylic acid. Like discussed in alcohol lecture, that when your aim is just limited oxidation, you don't want an acid to be formed. You don't use normal oxidizing agent like permanganate or chromate in acid. Rather, use PCC, pyridinium chlorochromate. But whenever you're using normal oxidizing agent, there is high tendency that your primary alcohol is going to end up forming carboxylic acid. Oxidation of double bond using permanganate is going to form carboxylic acid. Now, when I have symmetrical alkene, I'm going to form 2-carboxylic acid. But when I have asymmetrical alkene, I can form ketone and carboxylic acid. So for formation of carboxylic acid occurs only with symmetrical alkene. Looking at the last structure is like trying to tell you the mechanism of formation of this carboxylic acid. So whenever I'm using symmetrical alkene, go to where these alkene are connected by double bond, where you can split them into two and they're giving you the same thing by your left and your right. It means that the compound is symmetrical. So the place you have double bond, you're going to add oxygen, making it aldehyde. That's why the first thing we're going to form is aldehyde, which further oxidizes to form carboxylic acid. Hence, we are going to have 2-carboxylic acid with symmetrical alkene under oxidation, vigorous oxidation with potassium permanganate. Hydrolysis of nitrile. Whenever nitrile are hydrolyzed, whether acidic or basic hydrolysis, the end product is carboxylic acid. If it's acidic hydrolysis, you form your carboxylic acid. But if it's basic hydrolysis, you're going to form an intermediate which will finally hydrolyze again using acid hydrolysis to form your carboxylic acid. So hydrolysis of nitrile will always form carboxylic acid. When esters are hydrolyzed, we are forming acid and alcohol. Remember, esterification reaction involve acid and alcohol to form an ester. So opposite of esterification is hydrolysis. Remember, whenever during esterification you're going to form water. So the reversible reaction is also hydrolysis to form an acid. But if you're using base, that is sodium hydroxide, you're going to form an intermediate which is acetate. sodium salt of the acid, which under hydrolysis is going to form an acid. But if you're using acid hydrolysis, you're going to form your normal acid and alcohol that form the ester. Formation of acid using Grignard method. The first stage is using ALKYL halide under magnesium and anhydrous ether to form the Grignard reagent. Then this Grignard reagent is going to react with carbon dioxide, which under hydrolysis is going to form carboxylic acid. So the first stage is with ALKYL halide is to form Grignard reagent. Then in the presence of CO2, this CO2 is going to connect to the alkyl group to extend the carbon chain. Then under hydrolysis, we are going to, just like what happens when you're using Grignard reagent in forming alcohol, the same thing applies here. In this hydrolysis, the magnesium, which is electropositive, is going to have positive, while oxygen, which is electronegative, is going to have negative charge. So under hydrolysis, we have hydrogen ion and hydroxyl ion. So the hydrogen ion is going to come and bond with oxygen to form the acid, while hydroxyl ion is going to bond with electropositive magnesium to form a byproduct, which is not always important in this reaction. Under carboxylation of alkene, in the presence of carbon monoxide and under phosphoric acid as catalyst, my alkene forms carboxylic acid. This carbon monoxide is going to cause the carbon chain of alkene to be extended by 1. So that's why we have ethylene, which is ethene, having 2 carbon. Under carboxylation of alkene, we are going to have propanoic acid. So because of the carbon monoxide, the carbon chain is increased by 1. The mechanism is as shown. In the presence of carbon monoxide, remember when you split the bond, the negative is going to be on any of the methylene because it's symmetrical. So after then, my carbon monoxide is going to be added in the ring. Under hydrolysis, acid will be formed. From malonic ester, ALKYL halide is going to react with sodium malonate. In that reaction, sodium halide will be eliminated to accommodate the alkyl substituent in the malonate, which under hydrolysis, in this case acid hydrolysis, is going to form carboxylic acid. But the nature of carboxylic acid formed here is dicarboxylic acid. Hence, there is need for decarboxylation. Decarboxylation is removal of CO2. When removed, we form a monocarboxylic acid. Chemical properties of carboxylic acid. These carboxylic acids are weak acids. Organic acids are always weak acids. So, substituents with high electronegativity, such as hydroxyl, halogens, and ammonia, when they are close to this carboxyl functional group, they are going to increase the acidity of the carboxylic acid. That is why this also can be validated from the pKa. Remember, the lower the pKa, the more the acidity. The closer this halogen to carboxyl functional group, the stronger the acid. And the more the number of the halogen on the carboxylic compound, the higher the acidity. The first one is normal acetic acid, there is no halogen. And when there is halogen, one halogen, chlorine, it becomes stronger, 2.86. And when the halogen is increased, the strength of this acid becomes stronger. And when all the hydrogen is replaced with halogen, the acid becomes very strong. So the presence of this halogen increases acidity. The proximity and the number will also be considered when determining the acidity in absence of pKa value. But when there is pKa value, it's easier to determine the strength of an acid. These acids can also react with bases. When they react with base, they are going to form salts. So the base can be sodium hydroxide, potassium hydroxide, or ammonia. Other stronger bases can also react to form salts and water. In terms of reduction, carboxylic acid can be resistant to some reducing agents. There's powerful reducing agent like lithium aluminum hydride can reduce carboxylic acid to primary alcohol. So reduction of carboxylic acid leads to primary alcohol, and oxidation of primary alcohol is going to form carboxylic acid. So oxidation and reduction are reversible reaction. But you can't reduce acid with any other reducing agents. So I cannot use hydrogen in lithium palladium to reduce carboxylic acid. I can only use lithium aluminum tetrahydride. I can also use borane. The next reaction is esterification reaction called Fischer's esterification. In this reaction, carboxylic acid will react with alcohol under sulfuric acid as catalyst to form an ester. This is the best way of preparing ester. Looking at that, this is a reversible reaction, meaning that this ester formed can also revert back to the reactants, which are carboxylic acid and alcohol. Next reactions of carboxylic acid is decarboxylation. When carboxylic acid are decarboxylated, they form alkane. So decarboxylation is loss of CO2 from carboxyl group. When it's lost, my carboxylic acid becomes alkane. The reactions of carboxylic acid. Carboxylic acid can react to sodium hydroxide to form a salt. They can react with sodium hydrogen carbonate. All this. So in salt formation, carboxylic acid will react with base to form salts. Carboxylic acid can also react with inorganic halides like phosphorus pentachloride, phosphorus trichloride, thionyl chloride. They can also react with phosphorus pentabromide, phosphorus tribromide to form the corresponding acyl halides. Remember in the slide of alcohol, we said that the best method of preparing acyl halide is using thionyl chloride, because if you look at the side products, they are gases which can easily be removed, unlike when you're using phosphorus halide. The byproduct cannot be easily removed. So the best method of preparing acyl halide is using thionyl halide, which is SOCl2. Carboxylic acid can also be employed in synthesis of amide. When carboxylic acid reacts with ammonia, a salt will be formed, which when heated forms an amide. So the easiest way, the method of preparing amide is reacting carboxylic acid with ammonia, and under heating, amide will be formed. Carboxylic acid can also be employed in synthesis of anhydride. In anhydride, two acids come together and water is eliminated to form anhydride. And this water cannot be eliminated without a dehydrating agent. And in this case, phosphorus pentaoxide is employed to remove water from 2 mole of carboxylic acid to form an acid anhydride. So if the acid employed is acetic acid, so we're going to have acetic anhydride. Remember, it must be similar acids to form anhydride. Like said previously, that esters can form when carboxylic acid reacts with alcohol. It is worthy of note that in this water being eliminated, alcohol is going to release hydrogen ion, while acid is going to release hydroxyl ion to form the ester in esterification reaction. And this method is called Fischer's esterification, which is the best method of synthesizing or preparing ester in the lab. Esterification can also be obtained using diazomethane. In this diazomethane, what happens is that all the acid is being used, but nitrogen is being eliminated. Looking at the reaction, you realize that the terminal hydrogen is going to form methyl by forming bonding with the methylene of diazomethane, forming an ester. So at the end, nitrogen gas will be eliminated, which will, being a gas, can easily evaporate. So this is another method of esterification, but not as good as Fischer's method of esterification. So I can do esterification using diazomethane and also using alcohol with carboxylic acid. Like said in the previous slide, in reduction of carboxyl functional group, I cannot use sodium borohydride, I cannot use hydrogen in nickel, palladium, platinum. I can only use lithium aluminum tetrahydride. I can also use boron. In that case, my acid is going to revert to alcohol. Others are side product, which is reduction can also be done using boron. Boron is BH3 in tetrahydrofuran as a solvent under acid hydrolysis. This carboxylic acid, which is benzoic acid, can form benzyl alcohol. So my benzoic acid can form alcohol using boron as a reducing agent. Carboxylic acid can also be halogenated. In halogenation of carboxylic acid, it is the alpha carbon that is being halogenated. The alpha carbon is a carbon that is next to the carboxyl functional group. So that's why we call it alpha halogenation. The alpha halogenated acid is stronger than normal carboxylic acid. How do I identify the presence of carboxylic acid in the laboratory? The simplest method is using sodium hydrogen carbonate, also called sodium bicarbonate. In that case, there is effervescence and CO2 is being evolved. This is also confirmed by passing this gas through lime water, and lime water will turn milky. So sodium hydrogen carbonate is used in identifying the presence of carboxylic acid in the lab. Next is fragrance smell. When an unknown sample is added alcohol and drops of conch sulfuric acid, when there is fragrance smell, is an evidence that an ester is formed, meaning the compound is carboxylic acid. Next method is using fluorescence test. The presence of green fluorescence is a confirmation that the unknown sample is an acid. Acid is not just prepared, it's also very useful in nature. Acetic acid is useful in perfume, in plastic industry, in also ester synthesis, which means acetic acid is very useful in preparation of fragrances. Lactic acid is used as food preservative, is also a flavoring agent. We talk about tartaric acid, which is added to carbonated beverages. Citric acid, but we are talking about salicylic acid, which is used in treatment of acne and dandruff. So carboxylic acid are also very useful and being used daily in our lives. I encourage you to listen to these slides all over and all over again. Don't just listen once and you said you've listened to the slide. The more you listen to this, the more they become part of you. So when you enter exam hall, you write without stress. I wish you success in your 213 exams.